Hello and have a good day to Dr. Jiang. My name is Jhing with metric number of 181091343. And my individual project is simulations on the parameter of the three-phase YY system. Now I would like to start with my introductions. As we know that the electrical system can be connected in single-phase power supply or three-phase power supply. And this individual project is focused on three-phase power supply. The power supply can be connected in delta connections or Y connections, and both connections provide four possible circuit diagrams, which is delta Y, delta delta, YY, or Y delta. And my project is focused on YY electrical system. Next, this is the circuit diagram shown for the three-phase YY connection with four wires. The four wires include AA, BB, CC, and the one extra is neutral. From the TMB, we have 8 types of the rated line voltage, and my line voltage is 375 kV. And from the Malaysia standard, the frequency given is 50 Hz. So all calculations involve 275 kV with a frequency of 50 Hz. And the parameters involved is like phase voltage, line current, load line voltage, load phase voltage. Next, voltage drop. The voltage drop is the amount of the voltage lost in the electrical circuit and is normally occur due to the current flow through the impedance. And it is important as the engineer can control the parameter of the material such as length of the wires or the power factor. And the voltage drop shows that is it the electrical equipment safe to use, especially through our Malaysia standard, the voltage drop must lesser of equal to 3%, so it can avoid for hazard. Power, active power. Active power can calculated by conventional measuring method which require the phase load voltage and the line current. Next is the 2-watt meter method which require the load line voltage and the line current. And from the circuit, we can see they have 2-watt meter built by the ammeter and voltmeter. And the voltmeter is between the transmission loss and the load impedance, because we just measure for the active power in load impedance. And those method will calculate the power by using the general formula P equal to VI cos theta. And our objective for this project is to investigate and analyze the electrical system formations by calculation and simulations. And the second one is to evaluate the parameter of the electrical system in the context of transmission loss and load impedance, currents, voltage, and acceptable voltage drop based on BS 7671 or any Malaysia standards. And the last one is to evaluate and analyze the active power absorbed by the loads using 2-watt meter method and the conventional measuring method. Next, methodology and findings. Before we start our project, we need to plan it. So we need to find our rated line voltage and load, and then use the information to calculate the theoretical values such as the line currents, phase voltage, line voltage, power factor, voltage drop, and so on. And use these parameters to calculate the active power using the conventional measuring method and the 2-watt meter method. Next, since the PSIM just allowed the inductive load in unit Henry, so we need to convert it first before we draw the YY connections electrical system in PSIM. And then we find the component and connect it, then stimulate the parameter we needed, and record the data in the table. The IEEE report is written. Result and calculation of the voltage drop are present. Analysis, comparison, and discussion are done. As I said that we need to identify the initial requirements, so from the questions, we know that my line voltage is 275 kV and my metric number is 181091343. So I obtain the transmission loss and load. And the total is 124 plus 22 J ohm. Next is calculated for the theoretical value using the formula. And for the first one, phase voltage is equal to line voltage over square root 3. And we obtain the phase voltage with different phase angle. The next one is for the line current. We use a simple Ohm's law, which is V over Z, and the Z involves the transmission loss. And we obtain the line current. Same with the phase load voltage, and since E is load voltage, so the Z just involves the load. And we get the phase load voltage. And the next one is the power factor equal to cos theta. The theta is the difference of the phase angle of voltage and current. And we get 0.9939 lagging as it have inductive load. And we can say that the line current leads the load phase voltage by power factor of 0.9939. The next one is calculated the active power using the conventional measuring method. And as it is balanced generator and balanced load connection, so the power is same. So we can times 3 and get the total power of 385.8 megawatt. The next one is 2 watt meter method. So we need to find the load line voltage. Then we need to find our P1 and P2. P1 as normal, but for P2 we need to find for VCB, and we just get for VBC. So we need to plus 180 to obtain VCB and then get for P2. And we get the total by adding up both of the power, and then we get 385.78 megawatts, which almost the same if we round off it. Next, the voltage drop percentage. We must obtain the phase load voltage and then sub inside the formula times the percentage, and we get 35.32%. Then convert the inductive load from unit ohms to Henry by using this formula, and the frequency is 50 Hz, and we get in Henry. Then draw the three-phase YY system using the PSIM. This is our circuit look like. This is for the normal parameter, and this is for the 2 watt meter. So we need to draw it and then put the simulation control so that we can run the simulations. And we run the simulations, let's say the IAA and the IAN. So I click OK, it will have the waveform, and then I will click for RMS. I can obtain the value for the power, for the power factor. Same as the wattmeter, so I also simulate, and then I get the power. Next, record the simulated data and write the EEE report and compare it. From here, we notice that the line voltage is almost the same, phase voltage also. Also like load line voltage and phase voltage. They're not different much, just 0.1 difference. And then for the load line voltage, it's exactly the same, and for the INN is fulfilled, is 0. And for the power factor also, the simulator is 0.994, also the same, lagging. It shows the current led the voltage. The conventional measuring method, we need to obtain 3 power and then add up, and then we get the 386.24 megawatts. The next method, 2 watt meter method, we obtain 2 power and then add up, we get 386.25 megawatts. It's not different greatly, it's just different 0.01 megawatt. The last one is for the voltage drop percentage. The phase load voltage is not the same, so we need to find the average and then sub inside the formula. We get 35.32%, which is exactly the same with the theory. Discussions. The first is the relationship between the line voltage and the phase voltage. It can show as the line voltage is square root 3 greater than the phase voltage. As an example, we use VAN equal to 158.76 kilovolt, sub inside the value, and we get the line voltage is 274.98 kilovolt. So it is almost same with the simulated voltage, which is 274.99 kilovolts. The difference in the 0.01 kilovolt. The second one is the relationship between the line current and the phase currents. And since this is a YY system, so both are same. The third one is the calculations to obtain the current and the voltage. We use the simple Ohm's law, which is V equal to Iz. And the Z is involved the transmission loss. The calculations versus the simulations. The calculated data can be said is approximately same as the simulated data. Number 5. Power factor is equal to cos 6.34. And we get the lagging power factor as it contains the inductive load. So we can say that the current leads the phase load voltage with 6.34 degree. And this PF is fulfill the requirement of state in the handbook of the TMB, because since my rated line voltage is 275 kilovolt, which above the 132 kilovolts, so it will get minimum 0.9 and I get 0.9939, so it can be accepted. Number 6, voltage drop percentage for both data is exactly the same, which is 35.32. And since the acceptable voltage drop is below or equal to 3%, so this VDP is much larger than the standard. And this may be caused by the voltage share for the transmission loss and the load impedance. So the voltage at load impedance is different greatly to the voltage supply. And these high VDPs cause the low efficiency and easy to damage the electrical appliance. Calculation of active power. We use two methods to obtain the power, and the difference just 0.01 megawatt. And I suggest the method used is 2 watt meter method, as it is easier to conduct in the PCM, and we just need to find the request current and voltage, and normally it is more convenient if the Z is different. Conclusions. We can say that our objective is achieved, and we also learn to draw and simulate the three-phase YY system using the PCM. The second, we learn to calculate the parameter using the formula from the lesson. Third, learn and prove the relationship of the line voltage and phase voltage, which the line voltage is square root 3 larger than the phase voltage. Fourth, use two methods to obtain the active power, which 2 watt meter method, conventional measuring method. And I suggest that the method used to find the active power is 2 watt meter method, as it is more convenient. 6. Prove that the PF of this experiment fulfill the request of the Malaysia standard, as I use the line voltage of 275 kilovolt, so it at least get the 0.9 PF. 7. Show the system is not suitable to design the electrical appliance, as the VDP obtained is much larger than the standard. The last one, VDP encourage us to change the parameter to the safe level to avoid any hazard such as fire happened. That's all of my presentations. Thank you.